So far, we've talked about describing motion using like the kinematic equations. We've talked about explaining motion using Newton's laws. Right, Newton's laws lead to acceleration um, that went into the kinematic equations. And I want to talk about a new quantity that's harder to visualize and harder to measure than position, velocity, and acceleration, right? You can measure position, but with a ruler, right? And if you can measure a changing position, you can you can quantify velocity. And if you can measure a changing velocity, you can quantify acceleration. In fact, you can visualize those things, right? You can see that. Energy is not as easy to see, but the idea of energy is going to allow us to solve some of the same problems we've solved already in a different way, and it also lets us think about new and different kinds of problems. So we could ask the question, what is energy? And this is hard. One approach to this is to list types of energy. So let's list types of energy, and then we'll go back to what is energy. So let's ask types of energy. Well, there's energy involved in motion, right? So we could say energy. That's a little hard to read. Let's do it again. Of motion. Sometimes we call that kinetic energy. Maybe you've heard that before. There's thermal energy. There's energy associated with elevation, right? Sometimes we call that gravitational potential energy. Where else do we get energy? Well, we could talk about chemical potential, right? When you burn something, you get some kind of energy out of that. So that's chemical energy. A nuclear power plant works off of nuclear energy. And in fact, those last three are types of potential energies, right? So chemical energy really is chemical potential. Nuclear energy is really nuclear potential energy associated with the forces inside of the nucleus. So these are all potential energies. Let's do this. And thermal energy is kind of like random motion energy. So those top two, energy of motion, meaning kinetic energy, and thermal energy, are related. Okay, that doesn't answer what is energy. This is just a list of types of energy, right? What is energy? Well, one definition that we use is the ability to do work. That's not super helpful because then we can ask, what is work? I don't have a great like one sentence definition for work, but I do have a great equation for work. Work is force acting over a distance. When a force acts on an object over some distance, if it's the only force, if there's only one force acting on an object over a distance, that object will speed up or slow down, right? It'll accelerate. And that's how we know work was done on that object. In fact, what we're doing when we do work on an object, if there are no other forces acting, or really the other way you could say it is a net force acting over some distance, that would give you the net work done. Really what you're doing is you're changing the kinetic energy of that object. All right, and we'll get to that in a second. So work is force acting over a distance. Okay. So from that, we could come up with the units for work, right? What must be the unit? Well, force is a Newton, and a displacement is a meter. So a Newton times a meter must be the unit for work. Turns out we call this a joule, or capital J. You may have heard this energy, or this unit for work before. It's also the unit for energy. All right. Um, energy slash work. All right, it's a joule, capital J. You may have heard kilojoules before. You may have heard therms or British thermal units or calories or kilocalories. All of those are units of work and energy, but the SI unit is the joule. And every energy, all of these energies, gravitational potential, chemical energy, nuclear energy, thermal energy, those can all be related back to the joule. That is the SI unit. Okay, so so how do I know when work is done? Well, my equation here is not not entirely complete because I need to introduce one other idea, and that is this: that sometimes a force doesn't do any work on an object, right? So let me explain. So if I have an object here and a force acting on it, right? And I let this object move. Let's say it's on it's in empty space, right? So there's no friction to worry about. If I let this act over some distance, then work is done, right? I could say work is positive, right? Because if this object, let's say it starts at rest, at the end of this displacement delta x, it will have sped up, right? So it has more energy of motion, all right, or kinetic energy. We haven't defined kinetic energy yet, but we'll get there. Okay, so what if I had an object that was already moving? There's my initial velocity, and let's let a force act this way. There's my force. So the object is still moving to the right, but it's going to slow down. Right? Let's say it's a small force so that I don't have to worry about the object stopping and turning around. So in this case, the object is going to slow down, right? This is like reverse thrust, right? If you're, let's say, you can imagine a rocket trying to land on a planet, right? So the rocket is going down, but there's a thrust upward to slow it down so that it doesn't hit the ground going like really fast. Okay, so in this case, that work is negative, right? And all we did was we reversed the directions. Delta x is still to the right, but now the force is to the left. Okay, let's think about another example. Here is here's a block sitting on the ground, right? And let's say I apply a force that is like this way, right? So even if there's no friction, part of this force is moving this box to the right, and part of this force is just pushing the box into the ground, right? So if there is no friction, there will still be a displacement this direction, but not all of that force is doing positive work. Only part of the force is doing positive work. In fact, let's make this go away and say, if I put some axes here, only the part of this force that is parallel to the delta x is actually doing any work. So here's like a theta. So I'll say work is positive, but only part of F is doing it. In fact, in this case, I can figure out it's the parallel part, right? So it's, in this case, its work is force parallel times delta x, right? That's actually a more complete version of this equation. We could also write that in terms of the angle here, right? So F parallel delta x, or F cosine theta. Oops. No. Delta x. I think maybe in the handout I say F delta x cosine theta. Let's write it that way. No. Okay, this is a satisfactory definition for work. So again, F parallel delta x. That means if the force and the displacement are parallel, the work is positive. If they're anti-parallel, meaning pointing opposite directions. So when I say anti-parallel, I do not mean perpendicular. I mean pointing in exactly the opposite direction. The work is negative. And if it's anything in between, the work could be positive, it could be small, it could be maximum, it could be negative, it could be zero, right? Imagine a cat is sitting on this box, right? I don't know what it is with cats, but there's my cat sitting on this box. That cat is applying a normal force to the box, pushing down. But that's at a right angle to delta x, right? So F delta x cosine theta. Theta is 90, so cosine 90 is 0. That force doesn't do any work on the box. Okay. Let's look at a couple examples. In fact, it's example 1 in the handout. So a box is accelerated along the floor for a distance of 12 meters with 250 Newton force directed 12 degrees below the horizontal. How much work is done on the box by this force? Okay, so we can draw a picture of this. Here's our ground. Here's the box. And this force is acting, let's apply the force right here, 12 degrees below the horizontal. So there's my force. The horizontal is like right here. That angle is that 12 degrees. Right, so F parallel is this guy. And the box is going to move. In fact, it's moving, we're told, 12 meters. So we could collect some of this stuff. There's 12 meters. Theta is 12 degrees. And the force is 250 newtons. And the question is, how much work is done? So I can already tell you the answer needs to be positive, right? Because the force is ultimately causing acceleration along this path, but I'm going to have to include this 12 degrees because it's not, the force isn't being applied in the best possible way. So let's write that down then. So work is F parallel times delta x. And F parallel here is F cosine theta, right? So F cosine theta delta x. So plugging all of that in, 250 newtons times cosine of 12 degrees times 12 meters gives me 2,934 newtons times meters. And again, a newton meter is a joule, so I'm going to round that to 2,900 joules, just so I have two sig figs. Okay. Except I blocked out some of the next problem. Okay. So the next question. A 20-kilogram child runs along a wooden floor at 0.75 meters per second. He slides to a stop in 1.2 meters, how much work did the floor do on the child? Okay, so have you ever slid along the wooden floor with socks on? Right? What's happening here? The force that's slowing him down is friction. So let's draw a picture. There's my child initially moving at 0.75 meters per second, right? Slides to rest. So V final is 0 in a distance of 1.2 meters. Delta X is 1.2 meters. And the child weighs, let's say, mass is 20 kilograms. So that's not a weight, that's actually a mass, right? And the weight would be mg. Okay. So the friction acting here, friction acts back this way. It's kinetic friction. And I don't know the coefficient of kinetic friction between the child and the floor, so I can't use F sub k equals mu k times the normal force. But I do have enough information to figure out what the acceleration is, right? So my procedure here, so again, ultimately what I'd like to do is the work done is a force times delta x, force parallel. In this case, it's going to be the frictional force times delta x times a negative sign. And if I wanted to, let's move all of that over a little bit. If I wanted to, I could say times cosine of 180 degrees. Do you see that they point, the displacement is to the right and the friction is to the left. That cosine of 180 is going to give me that negative sign. Okay, so I need the frictional force, and to find the frictional force, I'm going to find acceleration first. So let's sketch that out. Find A, and then I'm going to use F equals ma to find that frictional force, because that's the only force causing that acceleration. So how do I find acceleration? Well, look at this. V final squared equals V initial squared plus 2a delta x. I know delta x, I know V initial and V final, so that's going to do it for me. Let me move this whole thing up just a little bit so that I have space to do the last line right underneath. Look at that. Okay. So V final is 0 squared. V initial is 0.75 meters per second squared plus 2 times a times delta x is 1.2 meters. So if I do all of that math, what I get is an acceleration of, put it over here, minus 0.2344 meters per second squared. Minus 0.2344 meters per second squared. Okay, and I'm going to keep all those digits because that's an intermediate step. I'm running a little bit out of space. No. I'll just move that down here. Not in love with it, but that's okay. So the next step is to find, let me underline this so that, the next step is to use Newton's second law to find the frictional force. So F equals ma. In this case, it's the frictional force which is acting to the left, so it's negative frictional, negative times the magnitude equals mass times a. And that mass is 20 kilograms. The acceleration is minus 0.2344. So if you do that math, you get 4.6875 newtons. So the frictional force is 4.6875 newtons. By the way, when we introduce the idea of kinetic energy, this problem will be so much easier. You'll see that. You'll see that. Okay, so there's my frictional force, and we are almost there. The last step here is to fill out work, right? So then work equals the frictional force times delta x times cosine of 180. Okay, so the frictional force is 4.6875 times the delta x is 1.2 meters times a -1. Oh, come on. So what I get when I do all of that together, that's a -1, is minus 5.6 joules. And here I am rounding, because this is our final answer. Okay. Yeah, that was a lot of work. Again, there is a theorem that will develop in the very near future that will make this problem so much easier. Okay. One last question, and then we'll call it good. So a student carries her 1.5 kilogram physics book across the room with that has a width of 10 meters at a constant rate. How much work does she do on the book? Okay, so what does this look like? There's the physics book, right? And she's walking at a constant rate across the room. So we could label that delta x is 10 meters. What is the force she's applying to the book? Well, she's applying a normal force, right? It's the same normal force at the beginning and the end. And the velocity is constant. So this book does not speed up or slow down. It does not change elevation. So there is no work done on the book, right? And we can calculate that. We can say work equals force times delta x times cosine theta. But theta is 90 degrees, right? So that's going to give me, right, F normal times this delta x times cosine 90 degrees. That's 0. 0 joules, or orange juice. Right? So that feels weird. Like, it doesn't cost me 0 energy to walk across the room with a book. Right? But that's not what the question is. The question is how much energy is transferred to the book. Because when work is done on an object, energy is transferred to it. And in this case, the book has not gained any energy of motion. It has also not changed elevation, and we'll see that matters when we talk about potentials. So, look forward to the next video where we develop new and different ideas.